So what happens as soon as we have a sector like this for memory? Well, it means that we now have a metabolic trade-off. We've gotten free energy from the environment, and now we have to decide how to use it. We can allocate it to perception, so getting information and then acting on the environment on the basis of that information, or we can allocate it to memory. And if I have a fixed amount of free energy, I can sort of turn a knob between perception and memory and try to find a place that's good. But if I want to keep getting information from the environment and processing it, I better not spend too much money on memory. So what do systems do? The solution we see over and over again is they coarse grain their memory. By coarse graining the memory, I write fewer bits to represent a past event, so I represent it at lower resolution. And you see examples of this trade-off everywhere. In your computer, you don't coarse grain your memory. You want to keep an exact record. But up here, you do coarse grain your memory. And in fact, all organisms that I know of coarse grain their memories. So they bias their free energy budget toward getting information. Okay, so now let's think about a system that doesn't just look at its environment and remember things. It looks at its environment and it sees particular objects that are distinct. So I look out at you and I see a bunch of people, I see some tables and chairs, I see lights, doors, walls, all this stuff. So I'm identifying a lot of objects right now. And if I want to identify an object, then I have to do two things. I have to have some kind of detector that says this is an object and this is the same object next time I look, and it's the same object next time I look. But I have to have another detector that says, okay, there's some states that have changed. And you can see this really clearly with the scientific instrument, where if I tell you to go in the lab and read the voltmeter, the first thing you got to do is find the voltmeter before you can read it. And then reading it is a different process that assumes that you found it. So every time I see an object, I have to allocate two sectors of my boundary. One for what I keep constant to identify the object, and the other one to look at its variable, the variable that's of interest, or the variable that I can measure without seeing it as a different object. And in physics, the variable is always called a pointer state because of old meters that had pointers. So I call these the reference sector and the pointer sector. So if I see an object, I've automatically made two more sector divisions in both my information space and my memory space. Because in my memory space, I've got to write down that I saw this state of that object. So I have to write two distinct records, and I don't want them to get mixed up. Okay, and all of this requires free energy because I've got to keep these sector boundaries fixed. So now I can think about identifying more than one object. And anytime I deploy operators that can't be deployed at exactly the same time, I've got to break this symmetry again and write a different set of sectors in my memory. And I use the word non-co-deployable here because I may not be able to deploy these operators because they really don't commute in some fundamental physics way, like up spin and sideways spin. But I may not be able to deploy them simultaneously just because I don't have the free energy to do it. And that's just as bad, right? If I don't have the free energy, I can deploy this one, and then I have to wait a little bit and deploy that one. I can't do them at the same time. And it turns out that if you can deploy two operators simultaneously you can just do the and or the or and have one operator. But if they're not co-deployable, then you have to represent them separately and define their own sectors. So there are many, many, many examples in human perception and other perception and physical measurement and on and on and on of operators that you can't deploy simultaneously. So what does this do? It makes this trade-off much, much more complicated because it's cut the boundary up into many sectors. And given a free energy constraint, it means that you have to make decisions about what sector you're looking at. And you typically don't want to completely ignore sectors of your boundary, so you just don't focus attention on them. So what this tells us is that any system essentially that can look at its environment in more than a couple of ways and has memory has to have an attention system, even if it's a very simple attention system. And attention here just means control of what I'm deploying to look at the environment, and control of how I move free energy resources around between my computational resources. Okay, so what does this tell us about S's internal structure? And I'll spend the rest of the talk on this question of what can we learn about any system, any generic physical system that has these symmetry breaking capabilities. And in particular, what can we learn about any organism, since organisms break all of these symmetries? Well, what we can first rely on is a theorem. This is a quantum theoretic theorem. And I should back up and say that a feature of this whole discussion is that when we look at the state space, there's no requirement that it has any geometric degrees of freedom. So I'm doing this in a representation that doesn't assume anything about space-time. So in the classical FEP, you typically assume that the parts of a system are located in different space compartments, and that's part of what keeps them conditionally independent. But in quantum theory, you don't need to do that. You don't have to assume anything about space-time at all. And as we'll see, we're going to get space-time out of this instead of having to put it in from the beginning. So we have this theorem that says if I have two computational resources, I'll call them Q1 and Q2, and they can't be deployed simultaneously, then we have to keep them separate inside the system. And by separate, I mean not entangled. Because if they're entangled, I won't be able to distinguish them. But I've made the assumption that I can deploy them individually. So they've got to be separate. They can't be entangled. And that means that they're compartmentalized in a way that forces them to only communicate classically. So they can only communicate by exchanging bit strings if they're not entangled. Well, what does that mean? It means I have to have boundaries inside my system that divide these compartments that can only communicate classically. So physics alone, with nothing else, if you assume you have the cognitive or the computational capability to break the symmetry of your boundary, the physics gives you compartmentalization with boundaries that can only be crossed with classical information. And here's a very simple stripped down system that has a memory compartment and two compartments that let it look at its environment and think of these as both being split into a reference detector and a pointer detector. So this is a little thing that can identify two different objects and remember something. And even at this level of simplicity, because of this theorem about classical information and compartmentalization, you have to have a control compartment, which is separate from these perception and memory compartments, and that manages this attention system, which is allocating free energy and saying, don't do this, do that now. And some colleagues and I have done a general theory of how to represent these control structures, and it turns out you can do it with tensor networks, and you can describe control with tensor networks only if you have this kind of compartmentalization that keeps things that can't be co-deployed in unentangled compartments that can only communicate classically. So the theory holds together quite nicely, and you get this compartmentalization for free. So let's look at a single compartment and what its relation with its environment is. And I've picked one of the compartments that looks at the external environment, E, but since it has this internal boundary that enforces classical communication, it also sees other internal compartments that are like it, i.e. other compartments that do perception and action. And then it also sees this compartment behind it that does control. And so if you think of this in a free energy principle way, where you're interested in how is the variational free energy, so how is surprise or unpredictability or risk, or however you want to describe the VFE, how is that distributed across the boundary? And in the case of this little compartment, the bit that faces the exterior environment is going to encode the highest VFE because it's the least predictable system. The compartments on both sides are compartments that are a whole lot like me, right? They do the same thing I do. So it's easier for me to predict what they're going to do and how they're going to behave and what kind of information they're going to send across the boundary because they're a lot like me. And I don't need to know they're a lot like me. I just need to recognize that I'm not getting a lot of surprisal from those compartments on the side. Now, the control system behind me may work in a completely different way than I do, although from a very generic point of view, you can represent it using the same kind of mathematics. So it's probably got a little bit higher VFE than the ones on the side, but a lot less than the one in front, i.e. the environment. So if these sectors behave differently, and I have a way of detecting what VFE is on what part of the boundary, then from my point of view as a little compartment, I can distinguish between the parts of my environment that I'm not too worried about, my cousins, if you will, and the part behind me that occasionally tells me what to do, and the part in front of me that's very uncertain that my job is to measure and act on. So here's a more familiar view of what one of these systems looks like. There's an outside environment, there's an outer ring of things that face that outside environment, and there's an inside that does all the control functions and allocates free energy. And one of these outside compartments, of course, is the free energy supply, the power supply, that doesn't have a measurement function. It's just a source. And this picture applies at whatever scale you like. I haven't made any scale assumptions. So these compartments can represent pathways inside a cell. They can represent cells inside an organism. They can represent tissues. They can represent organisms in a community, whatever you want. The FEP is a scale-free model of any physical system that's interacting with any environment.